Hello everyone, welcome back. Let's now look at section 4.2, the least squares regression line. Part 1, the least squares estimation. And in short, we call that LSE. Let's still recall the size and selling price example. So selling price is the outcome variable. And then we also call that response. And then we refer the size as the explanatory variable, which we also call predictor. The explanatory variable is used to explain or predict the value of the outcome variable. So in this example, based on the size, we want to explain the selling price. And then we can, of course, draw the scatter plot. So selling price is the outcome variable, or we call response. So now when we draw the scatter plot, we prefer to put the response in the y-axis, and then we want to use the letter y to denote the values of the outcome variable. So that's y, and then again is the response. And then x is the predictor. So here we have size, right? So explanatory variable or predictor. We use x to denote the values of the explanatory variable. And then when we now draw the scatter plot, we prefer to put x in the x-axis and the y in the y-axis. And then we have this scatter plot. Plot A and B, they have the same scatter plot. It's just when we use this line to describe the trend of the data, it makes more sense compared to this one, right? And because this line kind of have all the data gathered around, and then with the minimum squared distance. And for this one, if we use this line to represent the trend, so this line to represent the trend, which is not very good. Because the line is far away from most of the data, right? Most of the dots. And maybe one dot stay close to the line, but all others, it's too far away. So the reason we call it this section the least squares regression line is because we want a line to describe the trend of the data that has the minimum squared distance. Okay, then if we want to use a line, right? For the line, we have equation for the line, right? That's y equals a plus bx. And then a is the intercept and b is the slope. Like that's a standard equation or formula for a line, right? Mathematically. And then for here, we just changed the notation a little bit for that line. So the equation of the least squares regression line for predicting y from x is y hat equals b naught plus b1x. So here we call it y hat. The hat means is the estimated or predicted value. And then the b naught is the intercept here, and then b1 is the slope. And then we have a way to calculate that b1 and b naught, the estimated, we call those estimated coefficients. So where b1 equals r times sy over sx. So r is the correlation coefficient, sy is the standard deviation of y, and then Sx is the sample standard deviation of x. So B1 is the slope, and B0 is the y-intercept. So B0 is y bar minus B1 x bar. So mean of y minus B1, we calculated that already, and times x bar. So that's the formula. And again, the reason we use y hat to be the equation of the least square regression line is similar to sample mean and population mean. We don't know the population mean, so we estimate it, use the sample mean. Here, we don't know the true line, so we estimate it, use that y hat to find the best possible line we can get. Okay, and then still we're using this size and selling price example to calculate or to find the equation of the least square regression line. So mainly we need to find what beta naught and beta 1. So we can calculate x bar and y bar, standard deviation, sample standard deviation of x, sample standard deviation of y. And then based on the information, we can calculate our R. So we're the correlation coefficient, already done that, right? So B1 is R times SY over SX. So that's actually 0.9006 times SY, which is 29.6841 over SX, right? 269.4936. SY over SX times R. So that gives us B1.0992, which is the slope. And then B0 is just Y bar. So 447.0 minus B1 0.0992 times 2891.25, which is X bar. So that gives us that 160.1939. Now we can plug in the two numbers to that equation, right? So y hat, so that's why we have that y hat equals 160.1939 plus 0.0992 x. So y equals a plus bx. That's the equation for a line. So that's what we got here, the least square regression line. Okay, so that's how we do it by hand, right? And then if we want to use this R calculator, again, we type in X and Y data, and then find B0 and B1. So the estimated coefficients, right? So coefficient, we just use COEF, and then open parentheses, close parentheses. In between, we say linear model. So that's the least square regression line. So it's one type of the linear model. So in R, we say linear model YX, right? Y tilde X. So that'll tell R to calculate that B1 and B0 for us. So intercept is the B0, right? So this is B0. And then the slope is B1. So that's what we get from the R calculator. And then if we want to draw a scatter plot using the calculator, so we just say plot X and Y. So we first describe the X-axis and then the Y-axis. So don't forget the order. So that's what that's what we got, right? Y in the Y-axis and then X in the X-axis. And then AB line means we want to draw the least square regression line. So that's the least square regression line across the data. So and this one give us the smallest vertical squared vertical distance. Okay. And 4.2.2 prediction. So we can use the least squares regression line to predict the values of the outcome variable if we're given the value of the explanatory variable. Of course, it has to be within a range of the data. For example, here So all the data, so in x-axis stays from that 2500 to 3200. That's the range of the data. So when we do prediction, we don't want to go beyond that range because we don't know the shape or the data trend beyond the range. So within the range, we can do the prediction. The value I had that is computed when substitute the x value is the predicted value. Let's look at the example here. So predict the selling price of a house of size 2891.25 square feet. So when we have the x value, right, x equals this number, and then y hat, we have the least square equation already, the line equation. So just plug in. So 160.1939 plus 0.0992 times that plugged in x value, 2891.25, so which is 447. So note, this is happen to be x bar, and this is happen to be y bar. That means what? When we plug in x bar, we got y bar. That means the least square regression line goes through the point of averages. So when you plug in x bar, what you got is y bar. And then that's how we get the predicted value. So for any other number between the range of the data, you can plug in and then get the predicted value. 4.2.3 interpretation. So we have 3 interpretation here. So interpretation of the predicted value y hat, interpretation of the slope b1, and the interpretation of the y-intercept b0. So let's look at the first one, interpreting the predicted value y hat. The predicted value y hat can be used to estimate the average outcome for a given value of the explanatory variable x. Or we say for any given value x, the value y hat is an estimate of the average y value for all points with that x value. For example, we want to use the least square regression line to estimate the average price of all houses whose size is 3,000 square feet. It's not necessary we only have one house at this size, right? There could be multiple houses. They're all at 3,000 square feet. And then, but the prices, there's some variation in the price. So we say y hat is we calculate y hat and to be 457.8 when we plug in 3,000, and then the interpretation for this y hat then gonna be we estimate the average price for the house of 3,000 feet to be $457.8 thousand. So if we draw a scatter plot, right? Let's say this is 3,000. That means we have some data here, right? So this example, we only have like 8, n equals 8 sample set, 8 pairs of data. But we could have more, right? When we have more data, so it's possible that you have multiple points at this 3,000 level. That means for 3,000 square feet house, the price are different, and then that gives us a distribution at this level, right? So the mean of that is the average of that is this much for 57.8. That's the interpretation of the predicted value y hat. Interpreting the slope b1. So if the x value increased by 1 unit, the y value will change by an amount equal to the slope of the unit. For the house pricing example, we have y hat equals b0 plus b1x, which is 160 plus that slope, right? So for every 1 unit increase in x, the mean of that y will change this much, right? 0.0992. So the interpretation is for every 1 feet increase in the size, the house price will change because we got a positive sign here. So we'll change positive $0.0992 thousand dollars on average. Okay, so if the increase is 150 units or 150 feet for this example. For example, we say the difference is 1750 to 1900. The predict price change will be 0.0992 times 150, which is 14.9. 14.9. Okay, so let's look at this one. So we have y hat and y hat star, right? For example, so y hat is 160.1939 plus 1750 plus 0.0992 times 1750. And this one, same thing for the intercept, right? 160.1939 plus 0.0992 times 1900. So that's 150 unit change, right? The y hat change is gonna be what? So we use y hat star minus y hat, right? That's the change, which is this one minus that one. Because they both have 160.1939, so that cancels out. So what we really have is 0.0992 times 1900 minus 0.0992 times 1750. So which is 0.0992 times 1900 minus 1750, which is 0.0992 times 150. That's how we get this for 150 unit, right? Just multiply 150. Okay, the last interpretation, y-intercept B naught. Sometimes this interpretation is not useful because B naught is y hat given x equals 0. So y hat equals B naught plus B1x, right? So when x equals 0, so that is B naught plus B1 times 0. So that's B naught. So B naught is actually a special case for y hat. So the predicted value of y hat. Why we say it's not useful? Because most likely it's outside the range of the data. So for this example, that means for the house with 0 feet of size, what's the price, right? So of course it's outside the range of the original data. It's outside the range, right? And another thing is it doesn't make sense when we look at size 0 house. Okay, that's all for this chapter 4. And if you have any question, please feel free to contact me at my email address. And thanks for watching.